Okay, thanks, Alan, for the introduction. So today my topic is KeenLab iOS jailbreak internals. The Userland read-only memory can be dangerous. So as many of you noticed that KeenLab demonstrated iOS 10.3.2 and 11 beta 2 jailbreak at MOSEC 2017. But the details of the vulnerability has never been revealed yet. So today I would like to take this opportunity to show the details of all jailbreak chance which the bug is involved. So first, about myself, I'm the security researcher and also the team leader at Tencent Keen Security Lab. And previously, my research covers on the browser vulnerability research, the exploitation, majorly on the Safari, Chrome, and the Internet Explorer. And now my focus moved to the Apple vulnerability research, mainly for the sandbox bypassing and also kernel privilege escalation. So today our agenda is like, we will firstly talk about the memory protection implemented by the modern OS. This is not a very interesting topic because it is there for many years. Next, we discuss about the iOS DMA features, including the previous research, as well as the implementation of the iOS IOMMU protection. And the next, because KeenLab did a lot of reversing work on the iOS GPU notification mechanism part, since it is not open sourced part of the iOS kernel. And with enough knowledge explained, we will finally talk about the bug, which includes two of them. The first one is in the DMA mapping feature vulnerability, and another is the out-of-bound write in the Apple graphics stack. After the vulnerability has been explained, we will talk about the exploitation with a demo, and then we will conclude this talk. So the first part is operating system memory protection overview. So modern OS actually implements the memory protection at the hardware level to mitigate the known attacks. They are introduced in different levels. For example, the translation block entry properties at the MMU level. So in this part, we will they introduce the NX, the non-executable bit, and also the PXN to prevent execution in the userland from the kernel side. And also the AP, which indicates access protection, like the read-only or write-only or execute-only memory. And besides that, there are also some of the mitigations like the KPP AMCC, which is also relating to the memory protection, but they are implemented in maybe deeper and lower level, which is not our scope of the talk. So among those memory protection mechanisms, Userland read-only mapping is a very old school approach to protect the Userland memory. It is very easily implemented, but very effective. There are three major scenarios of using such read-only Userland memory mappings. The first one is, for example, the executable memory in iOS is only read-only to prevent the attackers from overwriting the code at the very early stage of the exploitation. And along with some other mitigations like the code signing enforcement, this has made the iOS very strong in security. And the second scenario is the sharing memory. The second one is between process. For example, two processes share one physical copy of the memory. And in the third scenario, it is sharing memory between the kernel and the process. Memory sharing at userland makes the inter-process or user-to-kernel communication more efficient. This is because you do not need to use the traditional message send mechanism, like to call some syscall or to call some trap to send the buffer from the user to the kernel. And in that way, the server process or the kernel who owns that memory can trust it because he is the only one who can modify it. While the client side or the client process can only have the read-only process, which it is not possible to change the memory. Then the owner process or the kernel can eliminate the specific secret considerations such as the boundary check or the time of check or time of use issues. So its implementation at the MMU level is quite easy. It has in the TBE entry, it introduced the access protection bit where you can find the specification document on the right side. I will not look into it very detailedly. And when there is a way found to make the mapping writable, then the whole trust boundary of the memory will be broken. But you need to make sure that the memory is remapped into writable without marking them copy on write. Otherwise, another copy of the physical memory will be introduced and you are not able to mutate the original physical copy of the mapping still. And once that is done, then it can lead to privilege escalation. So in the process-to-process memory sharing scenario, it can lead to sandbox bypass. While for the process-to-kernel memory sharing scenario, when you are able to modify a read-only mapping, it is very possible for you to get a kernel code execution. iOS actually has its nature to prevent such writable remappings at its kernel code. You can see that once memory is mapped to the process using read-only, actually that mapping has a property called max protection. And that max protection is set no higher than writable. So that when you try to remap it as a read and write, the kernel will reject you immediately. But there is an exception when you specify copy on write protection properties. The remapping will be allowed, but another copy of the physical memory will be used. So you are still not able to modify that original memory. And of course, there is some historical issues. For example, the first one referred to the Android shared memory, making it writable and cause some issues. And the second one is on Windows platform. However, you will be noticed that on iOS platform, there is no such known issues. So we have to research on our own. The next part will cover the iOS DMA features. Because stronger and more abundant features provided by modern peripheral devices attached to the mobile device, DMA technology is introduced to enable the ability for faster data transfer. And interestingly, the DMA transfer will not involve any CPU, so that the access permission bits on the virtual addresses will be simply ignored. And the next question is, does the DMA transfer use the physical address? And if that is the case, no memory protection is involved anymore. But definitely it is not the case. Why? Because modern phones are First reason is that modern phones are 64-bit, while many of their peripheral devices remain 32-bit. In that case, address translation is quite needed to translate from 64-bit memory to 32-bit memory. And another reason is that we have to enforce the memory protection for the DMA transfer also, because if it is not there, it's not safe, right? Because of this, the IOMMU is introduced to perform this job. IOMMU, if on the 66-bit iOS device, the concept dot which refers to device address resolution table, is actually introduced and responsible to perform such address translation. And there are two kind of DMA, one for host-to-device DMA and another for device-to-host DMA. For host-to-device DMA, actually the system physical memory is mapped into the I/O space visible by the device. And in device-to-host DMA, it actually maps the device memory back to the OS virtual memory so that it can be identified by the operating system. And in the middle, 2017, Goole from Google Project Zero leverages the DMA features on iOS to achieve the firmware to host attack. And he compromised the Wi-Fi stack first, and then try to mutate some writable DMA mapping in the device memory, and it is also shared to the OS kernel memory. And the OS, the iOS, thinks that the DMA on the device is trustable. So it eliminated necessary boundary check. And finally, with the Wi-Fi stack compromised, it is very easy to modify that memory and finally lead to kernel code execution. However, such attack has some limitations. One obvious limitation is that such attack can only be performed in a short distance scenario because you have to compromise the Wi-Fi stack first, and that requires the attacker and the victim in the same Wi-Fi environment. Is it possible for us to make it long distance? For example, we have a browser exploit. We can try to launch it remotely by the browser exploit and together with a kernel privilege escalation bug. And of course, by utilizing the DMA related bugs. And that look like a very crazy idea because the DMA features are kind of very low-level implementation, which is mostly performed at the kernel level or the device level. It is not exposed to the Userland directly for sure. And it is still possible to think of it because there might be some indirect Userland DMA on the iOS. For example, on the iOS system, it has some JPEG engine. It is responsible to accelerate the encoding and the decoding process. And also in another scenario, there is I/O surface transform. And actually it is done by the hardware device called the scalar device. And we will look into the iOS transform feature a little bit. And actually KeenLab spent some time to investigate the iOS I/O surface transform feature. And before we study it, I'd like to briefly introduce the I/O surface and the I/O surface accelerator framework. So on the Apple world, the I/O surface represents a Userland buffer, which is shared with the kernel. And the Userland applications can create a I/O surface by providing a existing Userland buffer address and its length. So the code on the right side shows the creation process. So it first gets the properties of that Userland memory and then create a I/O memory descriptor with specific property as options. So here, if option K I/O direction out is set, it indicates that the Userland mapping is read-only. And once the read-only mapping is read-write, then option K I/O direction out as well as K I/O direction in will be both set. And the second framework is the I/O surface accelerator. And it's a kind of a Userland framework for, and it is only existing in iOS platform. And there are two important interfaces. One is IO Surface Accelerator Create, and another is IO Surface Accelerator Transfer Surface. The first one is responsible for creating IO kit user client connection, representing a IO Surface Accelerator client kernel object. And the second interface takes two IO surface handles, one for the source IO surface and the other for the destination, and do the transform. And there is one typical scenario of using this framework, which is the screen snapshot, where you have your destination IO surface as the receiving buffer, and the system maintains the IO surface for the frame buffer, and you make this transfer, and you can get a screenshot of it, of your current iPhone screen. And here is the low-level implementation of the IO surface accelerator. So on the top side, you can see there is an object called IO Surface Accelerator Client. Sorry. And the next component is the Apple M2 Scalar CSC, which is an upper-level driver, and it talks to the HAL, which stands for hardware abstract level. And the latter handles the device-independent dependent stuff, and provide the device-independent interface to the driver. And this whole object also creates 5 important objects, which stand for some important registers for that device. And that object whole also maps device memory from the device I/O space into the kernel virtual space via DMA, represents the device key registers. So here is the overall workflow for the transform. The first is the kernel will validate the parameter from the userland, and then it obtains the source and the destination IO surface address, and then it maps the IO surface buffer via DMA, and then it obtains the mapped address and sets some buffer, the device buffer, and then it starts the scalar device. And after the scalar device is started, then the kernel waits for the interrupt from the device to wait for its completeness. And after it is complete, everything is finished. So we are mostly interested on the DMA mapping part, and we are not interested in the other part. So this is actually done by the function set map prepared memory descriptor. And in that function code, you can see that a kernel object called IODMA command created with a very special IO mapper. And actually, that mapper is an instance of IO dot mapper, which is independent between devices to make sure that device and the device are separatedly in IO space addresses, so that one cannot interfere another. And using a very basic iOS utility called IORec, you can find this instance, the mapper instance for the dot scalar. And then the IO surface memory descriptor will be bounded to the IO DMA command. And the next step is to obtain the mapped IO surface address in the IO space. This is done by the calling the function generate IOVM segments. After you call this function, you obtain that address, and you can notice that V33 indicates the result address, which is in 32-bit. And after you get the source and the destination IO surface address in IO space, it's time to set the scalar device register. The key register is for source destination config control. This object is used to specify those addresses. And once you decide those addresses, you just change the you specify it via giving some value and set it into some specific offset in that mapped virtual memory. And after that, this is done. And the final thing is to start the scaler. This is very easy. You just need to set 1, which indicates the power on option. At the offset 1 to 8. And after you make that value to 1, the scaler device starts its starts its work immediately. And the final thing is for the kernel to wait for that device to finish working and issue interrupt event to indicate this has been done. Okay, so the next part I will cover for the IOMMU memory protection. So similar as the system MMU page table, the IOMMU also need to have the page table specification. However, unlike the CPU MMU, the page table document for IOMMU is not there. So you have to reverse the iOS start code to find out the specification. And we did it also. And coincidentally, Goole from Project Zero, Google Project Zero, also he did similar work. And here I just post a picture written by him on the right side. You can see that it has very similar specification as the CPU MMU. However, in his blog, he didn't mention that whether the IOMMU supports the memory protection or not. So here is a piece of his blog. He said it is unknown whether it can facilitate the read-only mappings. However, actually by reversing the code in iOS 11, we can get the answer. So IOVM map memory function is the entry point for mapping the memory in IO space, among which the map options parameter here has included the memory's protection bits in the virtual space. So here, the last 3 bits in that map options is translated to a direction value visible by the IOMMU. So here, for read-only mappings, it has the direction value 2. And the write-only mapping has the value 1. And the read and the write mapping has the value 3. We only need to remember this. And this variable finally reached the lower level implementation dot. And a function called set translation is finally reached. And from the code logic here, we can clearly see that actually the 8 and the 9th bit in the TTE entry are AP-related bits. So finally, we got the access protection specification in TTE for IOMMU on iOS. So here, the red part is AP bits, and 00 stand for read and write, 01 read only, and 10 write only. Next, we talk about the GPU notification mechanism. And on iPhone 7 device, we found that Apple Graphics provides with 128 channels for concurrent processing. Those channels have 3 categories: CL channel, GL channel, and the TA channel. And the kernel wraps join instructions from Userland and put them into those channels. And then kernel just wait for the GPU to finish processing. Because of that, a well-designed notification mechanism is very necessary because it needs to support for such high need for concurrent processing. Here is a brief architecture of the notification. The GPU task actually owns a stamp array representing a stamp status of each channel. So this memory is actually a representation of the uint32 array of 128 elements, each showing the last complete instructions stamp of that channel. And this stamp array memory is actually mapped not only to the kernel, but also to the userland. And of course, the userland mapping is read-only. And the kernel also maintains an array called the stamp address array. And this array is very simply constructed by the code below. And it contains an address array of 128 elements. And each element represents the virtual address of that mapped stamp status kernel address. And the stamp value of each channel is incremental upon each of the instruction processing completeness, which means once the processing is completed, then the GPU will update that stamp value, add it by 1. And in the kernel side, there is also an object called IOAxial event, which represents the expected stamp value in specific channel of one or one group of join instructions. So one axial event, IOAxial event, contains 8 sub-events. And one sub-event is 8 bytes in size, where its lower 4 bytes represents the channel index, and the higher 4 bytes represents the expected stamp value of that join instruction. So to test whether a join instruction has been completed or not, you just need to compare the expected stamp value with the value in that stamp array. So here is the code. It checks whether expected stamp is higher than the current last completed stamp value. If it is higher, then it continues the waiting process in the loop. But if it is smaller or equal, it means that join instruction has already been finished. Last but not the least, to improve the performance, some of the IOAxial event objects are also mapped into the userland, which is highly related to our bug. This is to make sure that the userland applications can understand the status of the current instruction and the current event without asking the kernel. So the userland app can also test whether the event has been completed or not. Okay, now with almost all the concepts well explained, let's discuss about the real vulnerabilities. So the first vulnerability is quite simple and obvious. On the iOS 10 and the early beta of iOS 11, actually the map options of the virtual memory is simply ignored by the Dart mapper. So from the code below, you can see that in the Dart code IOVMalloc, there is an option called map options, which indicates access protection bits of the virtual memory. And this parameter is never used later in that function. And in the lower level implementation, when the set translation API is called, you can find that the 8th bit and the 9th bit of the TTE are both set to 0, which indicates from our previous research, 0,0 means the read and write. It means for any kind of userland mappings or kernel land mappings, once it is translated and mapped into the I/O space, it is always read and write. And the second is the out-of-bound write vulnerability. So before I talk about it, I will explain the concept of the I/O axial resource object. Actually, I/O axial resource object is very similar in functionality as the I/O surface object, except that the I/O axial resource represents a shared userland buffer which would be mapped into the GPU task. And like the I/O surface object, we can also create the I/O axial resource object by specifying existing userland buffer in the userland applications. And during the initialization process, a shared mapping will be created. This shared mapping is called I/O axial client shared I/O. And this object contains I/O axial event array with 4 elements with the resource ID and its type information. And this object, the whole object, is mapped into both userland and the kernel. And of course, the userland mapping is read-only. And this address will also be returned to the userland applications, so the user will know the address of it. And the user application can also delete the created I/O axial resource by calling the method 1 in I/O axial shared user client. And after that, the test event function will be reached. And this function actually simply checks if each I/O axial event object in I/O axial client shared RO is complete or not. The code logic is quite simple. So first it checks whether the event's expected stamp value is lower than the current stamp maintained in an object called M inline array. And if yes, then it means the event has been completed. Yeah, and if not, then the code tries to fetch the latest stamp value from the device memory, which is referred to by the array mstamp address array. And after the latest value has been obtained, it does the comparison again. It does the comparison again and check if it is smaller or bigger, and decide whether this event has been completed or not. It looks very good at first glance. However, together with the DMA mapping bug, it is possible that we can modify the channel index here. And because this object is created by kernel and it's not possible to be mutated by the userland applications, kernel fully trusts it, and it doesn't perform enough boundary check. So once the index is mutated to a very big value, then of course we will have out of bound read to read out the array of the mstamp address array, and read out that value and then write to the m inline array, which is OOB write. Okay, so after the bugs has been explained, let's look into the exploitation. So exploitability of those 2 bugs depends on whether we can control the content for both M inline array and the M stamp address array. We need to control the content of both of them. It looks like a very hard task. This is because that both arrays are created in very early stage of the iOS booting process. And it looks impossible that we can put very controlled contents right after them. And also the second reason is that the size of the element of each array is quite different. The larger the index we specify, the longer span in the address of the reference array element we have. So that's not a very good news. And to exploit this bug, the memory layouting is a key factor. Before doing that, we need to understand some facts. The first fact is that kernel heap memory starts at a relatively low address. And the heap can grow linearly with more and more memory allocated. And the start address of the heap differs within tens of megabytes upon each boot. This is due to the early random value. And also, the address of M inline array and the M stamp address array are close with each other. And because of that, we can use a relatively large channel index, along with some technologies like kernel heap spray. We might able to increase the possibility to make sure the out-of-bound value of both arrays are under our control. So we definitely need a heap spray technologies. And luckily, this is not a problem because it is well published and you can find a lot of public articles about it. And on iPhone 7, under our test, we can spray around 350 megabytes kernel memory within the container sandbox applications. And after those two arrays are created, there are around 50 megabytes extra kernel memory allocated. So what conclusion we can get at this stage? The first, because the M inline array element size is 24 bytes, and the M stamp address array element size is 8 bytes. So if we can make sure that the index value multiplied by 24 is smaller than 400 megabytes, and the index value multiplied by 8 is larger than 50 megabytes, then we get the range of index is in this range. And if the index is in this range, we will have higher probabilities and higher possibilities that both out-of-bound value of both arrays are fallen into our sprayed data. And the next issue is, do we have arbitrary memory read and write? According to the nature of the bug, the arbitrary memory read is not a problem because M stamp address array element size is 8 bytes. With arbitrary index value, you can reach every D words within each page. However, the higher 4 bytes of a keyword cannot be read. But it is not necessary because usually to make it code execution, you only need to modify an address lower 4 bytes instead of the higher 4 bytes. However, the arbitrary memory write is more tricky because the M inline array element size is 24 bytes. Only one of its D word can be written. So it introduced a very interesting issue. Can we OOB write to an arbitrary offset in a 0x4000 page with the OOB array element size only 24 bytes? Before we solve this issue, we need to understand some facts. The first fact is good news. Thanks to the mechanism of the iOS XNU zone allocator, the base address of M inline array is always at offset 0xF0 or 0x20F0. Because it is field in some bigger object, which is 4,000 in 2,000 page, 2,000 in size, 0x2000 in size. And similarly, M stamp address array is allocated with 0x200 in size, falling into the calloc.512 zone. And this address offset within the 0x4000 page can all be the value, can be all values divisible by 0x200. So this is a good news. And similarly, we need to find find a way to write arbitrary page offset by OOB write on the M inline array. And this problem can be solved actually by a mathematics theory called the concurrence theory. So because 0xC000 is divisible by 0x4000, so all index values where the remainder values divided by 0x800 are the same. So we can always OOB write to the same offset in the M inline array. And within the fact here, we get the conclusion that given the index equals to 0x27f6 plus n multiplied by 0x800. So if that condition is met, we can always overwrite to the first 8 bytes in a spread page. And the next problem is to reach the arbitrary offset within the page. With the M be the offset of the page, we just ensure that index equals to this. And we can reach to arbitrary offset within the page. So we resolve this problem. So here, you don't need to understand all the stories of the concurrence theory, but you only need to remember the result, the conclusion. So when index equals to this, and it's within the range of this, then we are able to overwrite arbitrary offset in a page. And at last, we choose the value 0x9E6185, which means it can reach the offset 568 of 4000 page by writing this M inline array out of bound. And now let's do the first attempt of exploitation. First, we try to spray around 350 megabytes. And the logic is here. The test event function will reach the OOB values here. And then it try to put a guest address onto it and refer to the value of it in slot B. We call it the value value to read. And the value that is read will be finally written to the slot C at the offset 0x568, which is M inline array M inline array array. And by first attempt of the exploit, we then receive the OL message to see which message AW field, the address written field, has been changed. By checking the new value in that address, we can obtain two very important pieces of information. The first information is which OL message is allocated in slot C. And the second message, important information is which OL message is in slot B, because we can specify each OL message's VR field very unique. And after we got those information, we can perform the second exploit to bypass the ASLR. We do it by filling slot B with AGXGL context object. And that object is in calloc.8192. So it's very good. You can free the slot B and fill in at the same address. And then we change the GA value to this, which is the origin GA value minus 0x30. Because the base address of slot B is the V table of the first 8 bytes of the object is the V table address of AGXGL context object. So we exploit the bug again, and finally we got the lower 4 bytes of the AGXGL context V table. And after that, we obtain we bypass the KSLR. And finally, we need the code execution. So to get the code execution, we need to free the slot C and fill in with the object where its offset 0x568 represents some important object. And we found the AGX-GL context is the best choice also, because its offset 568 represents AGX accelerator object. By calling that user client's method 0, we can reach the function context finish. And the context finish will dereference that object's 568 as the keyword as a AGX accelerator object and use it to call its virtual functions. So by exploit that bug again, we are able to modify the lower 4 bytes of that AGX accelerator object and to modify it to any arbitrary value, and we can control the content of that new address so that we get PC control. So finally, I talk about the overall exploit overflow. So first, we create the IOAxial resource, and then we got the IOAxial event read-only buffer. We trigger the first bug to modify the M channel index to a bigger value. And then we prepare the memory layout, trigger bug 2, to obtain the index of the slot B and the slot C. And then we prepare the memory layout and for KASLR bypass, trigger the bug 2 and obtain the V table of AGX-GL context so that we bypass KSLR. And finally, we prepare the memory layout again for code execution to trigger bug 2 again and overwrite the AGX accelerator pointer in AGX-GL context. And after that, we can perform a ROP and get the task for PID 0. And then we perform post-exploitation to jailbreak. So after that, we got the task for PID 0, but it's the only first step of the jailbreak. We still need to break the AMFI to remount the root FS to read and write, and to perform the KPP and AMCC bypass, etc. And those are very well documented outside publicly, and it's not a scope of our talk. And we will show a demo of the attack. Yeah, so because of the time limitation, I will skip some parts. And first, we choose version 10.3.3 because I only have this version which can exploit this bug. Actually, the bug also exists in some early version of iOS 11 beta, but I don't have the device. So we click our application, we bypass the sandbox. Actually, there is no sandbox because we exploit the kernel directly, but we involve 2 bugs. So one, I think maybe sometime it can also, the DMA feature bug can also bypass the sandbox also. But here we don't use it. We just use it to change the M index, channel index. Yeah, after we bypass the KPP, then it do a respring, and finally we found that the CDI is installed on this machine with yeah, you can, yeah, but it's a little bit broken, but I think with trivial actions you can make it work. Yeah, and finally you can find the correct version of it. And finally I talk about the conclusion. So with the first release of iOS 11, Apple actually fixed the first bug, which is the DMA mapping bug. And it is actually fixed by adding the implementation of the read-only mapping at its start code. And however, the other OOB write bug remains unfixed up till now. And this is a very good example of how secret can be broken by very bad implementation, but with very good hardware design. And it makes possible a very complex exploit chain to achieve the jailbreak within the userland applications. At this stage, it is still safe to say that because with the first bug fixed, the trust boundary of the userland read-only mapping is back, so you don't need to fix the bug too. But it brings a problem to us. Should we actually trust the kernel, the userland read-only mappings? And of course, currently, there is no definite answer because I don't have another way to break that trust boundary. But at least in this talk, we demonstrated that the userland read-only mapping can be dangerous. It is possible that in the future, another bug is introduced and break this trust boundary again. And we make the whole exploit chain work again. It's very likely, and we never know at this moment. Thanks for listening. And if you have any questions.